To manage the integrity of a transaction, we need, number one, secure and unique account address. We need a standard approach to uniquely identify the participants in the decentralized network. Number two, authorization of the transaction by the sender through digital signing. And number three, verification that the content of the transaction is not modified. We use a combination of hashing and public key cryptography that we learned in the last two lessons to solve these problems. Let's start with the address of the accounts. Addresses of accounts are generated using public key, private key pair. Step 1. A 256-bit random number is generated and designated as the private key, kept secure and locked using a passphrase. Step 2. An ECC algorithm is applied to the private key to get a unique public key. This is the private-public key pair. Step 3. Then a hashing function is applied to the public key to obtain the account address. The address is shorter in size, only 20 bytes or 160 bits. Now that we have the account address, let's look at the transaction initiated by this address. A transaction for transferring assets will have to be authorized, it has to be non-repudiable, and unmodifiable. We'll first examine the digital signing process and then apply it to the transaction. Data is hashed and encrypted. This is the digital signature. The receiver gets the original data and the secure hash digitally signed. Receiver can recompute the hash of the original data received and compare it with the received hash to verify the integrity of the document. Now consider the transaction to be that data. Step number 1, find the hash of the data fields of the transaction. Step number 2, encrypt that hash using the private key of the participant originating the transaction, thus digitally signing the transaction to authorize and making the transaction non-repudiable. Step number 3, this hash is added to the transaction. It can be verified by others decrypting it using the public key of the sender of the transaction and recomputing the hash of the transaction. Then compare the computed hash and the hash received as the digital signature. If there is a match, accept the transaction. Otherwise, reject it. Note that for a complete transaction verification, the timestamp, nonce, account balances, and sufficiency of fees are also verified. As we discussed before, some of the main components of the Ethereum block are the header, the transactions, including the transaction hash or the transaction root, and the state variable, the state hash or the state root. Integrity of the block is managed by assuring that the block header contents are not tampered with, the transactions are not tampered with, state transitions are efficiently computed, hashed, and verified. Remember, the blockchain is supposed to be an immutable record. In Ethereum, the block hash is the block of all the elements in the block header, including the transaction root and state root hashes. It is computed by applying a variant of SHA-3 algorithm called Kechek in all the items of the block header. You will see a real example of Bitcoin block hash in the quiz associated with this module. A typical block has about 2,000 transactions in Bitcoin and about 100 transactions in Ethereum. We need an efficient way to detect tampering and validate the transaction efficiently. Hashes of transactions in a block are processed in a tree structure called Merkle tree hash that we discussed in an earlier lesson. Merkle tree hash is also used for computing the state root hash since only the hash of the chain states from block to block have to be recomputed. It is also used for receipt hash route. Remember the advantage over flat versus tree representation. If any transaction is to be verified, only one path through the tree has to be checked. You don't have to go through the entire set of transactions. Smart contract execution in Ethereum results in state transitions. Every state change requires state root hash recomputation. Instead of computing hash for the entire set of states, only the affected path in the Merkle tree needs to be recomputed. When the state 19 is changed to 20, that results in the path including 31, 41, and the state root hash 64 to be recomputed. Only that path is recomputed, not the entire tree. Now let's move on to block hash computation. Block hash in Ethereum is computed by first computing the state root hash, transaction root hash, and the receipt root hash shown at the bottom of the block header. These roots and all the other items in the header are hashed together with a variable nonce to solve the proof of work puzzle. Block hash serves two important purposes: verification of the integrity of the block and the transactions, formation of the chain link by embedding the previous block hash in the current block header. If any participant node tampers with the block, its hash value changes, resulting in a mismatch of the hash values and rendering the local chain of the node in an invalid state. Any future blocks initiated by the node will be rejected by other miners due to hash mismatch. This enforces the immutability of the chain. Summarizing, a combination of hashing and encryption are used for securing the various elements of the blockchain. Private public key pair and hashing are important foundational concepts in decentralized networks that operate beyond trust boundaries. In the last module, we learned about the use of public key cryptography and hashing for validation of transactions and blocks. After this module, you will be able to define elements of trust in a blockchain, security, validation, verification, and consensus, discuss consensus protocol, an algorithmic approach to add a new block and to secure the chain, explain trust in the robustness of the main chain, illustrate trust in managing exceptional situations such as hard fork and soft fork. Let us understand trust using a common everyday scenario in a centralized system such as an airport system. Say you want to fly out of the Buffalo airport. The airport authority will have pre-established a secure environment for people to arrive and depart. This establishes the base trust. Then there is additional trust once you enter and your passport and travel documents are verified, validated, and your baggage is screened. Even more trust in you is established when the airline staff checks your boarding pass at the gate and you enter the aircraft to fly. Now let's consider a decentralized system. There is nobody checking your credentials and certifying that you're trustworthy. Then how do you do it? You do it by using algorithms and techniques discussed in the last module. Let's examine how these will help address the trust issues in a blockchain. Similar to our airport scenario, trust in a decentralized blockchain is also about securing, validating, verifying, and making sure resources needed for transaction execution are available. This is accomplished by securing the chain using specific protocols, validating the transaction and blocks for tamper-proofing, verifying the availability of resources for transactions, and executing and confirming the transactions. The trust trail is defined by these operations. Validate transaction, verify gas and resources, gather transactions, execute transaction to get a new state, form the block, work towards consensus, finalize the block by the winner, and everyone add the block to their chain and confirm the transactions. We will examine each of these steps. Steps 1 and 2 are validate transaction and check resources. In the case of a Bitcoin, there are about 20 criteria that are to be checked before a transaction is validated, as discussed in Module 1. Similarly, in the case of Ethereum transaction, the syntax, the transaction signature, timestamp, nonce, gas limit, and sender account balance are validated before execution. The fuel or gas points and other resources available for smart contract execution are also validated. Transaction signatures and hash are also verified. Step number 3 is execute transactions. Merkle tree hash of the validated transactions is computed. This is in Ethereum. This is the transaction root of the block header. All miners execute the transaction for Ether transfer, as well as for execution of smart contracts. The state resulting from transaction execution are used in computing the Merkle tree hash of the states, the state root of the block header. The receipt root of the block header is also computed. In the next lesson, we'll continue to talk about the next step in trust trail, the consensus process.